In this video we will learn about tensors, which are a key mathematical tool for describing and implementing neural networks. Typically, you may not operate with tensors directly. They mostly operate under the hood, but it is useful to understand the math that's going on behind the scenes to get a stronger understanding of how the neural network operates. And it's also useful to be able to examine tensors directly, to be able to understand the data and be able to examine the network weights and biases if you wish. This video assumes some background on the part of the viewer. You should have some idea of how neural networks work. If you don't have that background, you can learn it from reviewing the article, The Magic of Neural Networks, History and Concepts, at this link. And you should have some familiarity with object-oriented programming in Python. Theoretically, neural networks could be implemented in pure Python. We could use Python lists to represent data and other lists of lists to represent the weights and biases for the network. And we could use nested for loops to implement the operation of multiplying inputs by connection weights. There are some issues with this, however. Python operates rather slowly, and also that would not result in very readable code. Instead, neural networks are typically implemented in libraries like PyTorch, for example, which use tensors. These libraries run much faster, and they also result in much more readable code. So what are tensors? Tensors are essentially arrays of values. And since neural networks are arrays of neurons and arrays of data, naturally tensors are a natural fit to describe them and implement them. A one-dimensional tensor is known as a vector. Here's an example of it written in mathematical notation. The values, the array values, are listed in just one dimension. It can be listed vertically or horizontally. Either notation is acceptable. Vectors are typically used to represent data in the network. For example, each numerical element could represent the input value to each corresponding input neuron in a network. A two-dimensional tensor is known as a matrix. Here's an example, an array of numbers laid out essentially in table form. For a fully connected network where each neuron in a given layer is connected to every other neuron in subsequent layers, a matrix is a good tool for describing the network of connection weights. Here we have an example with associated connection weights for each connection. And here we have a matrix describing the connection weights for the example network. Before we finish introducing tensors, let's use what we've used so far, what we've learned so far, to get an understanding of why tensors are so useful for describing neural networks. Let's introduce a two-element vector of data and run it through the network that we just showed. And here's our two-element data vector. Recall that neurons add together their weighted inputs and then run the result through an activation function. In this example, we will ignore the activation function to keep the calculation simple for the demonstration. This diagram depicts the network we showed before, processing the input vector data through it for a result. So here is the input vector that we showed, and the network takes that input and multiplies that input times the weights, and takes each weighted input and adds it together at each neuron. Takes each weighted input, adds it together at each neuron, and we get a resulting final output vector. These calculations show the processing that the network performs. The viewer can pause the video and verify these calculations and verify that they accurately represent what the neural network is doing, and we get these resulting values for the output. And here are those values as the final 3-element output vector. Most of you have probably learned about matrices in grade school and may recall doing matrix multiplication. And you may note that what we just calculated is identical to matrix multiplication. So here is the connection weight matrix, and here is the data vector. And doing matrix multiplication of the connection weight matrix times the data vector, recall we multiply this row against this column to give this element. This row times this column, add the two corresponding elements together to get this element, and then this row times this column, adding the multiplied elements together to get this element, and so on, resulting in resulting in this final output vector. This is why tensors are so important for describing neural networks, because tensor math precisely describes neural network operation. Note that this is a much more succinct notation than nested for loops would be. This is much easier to follow and understand. If, in addition, we were to introduce a nomenclature of bold lowercase for a vector and bold uppercase for a matrix, then the operation of vector data running through a neural network matrix that we described here with matrix multiplication is described by this very compact equation. The weight matrix times the data vector gives the output vector. And we will see later that matrix multiplication within PyTorch is a very similarly compact code equation. We've looked at one-dimensional and two-dimensional tensors. 3D and larger tensors are just known as tensors. Only the one-dimensional and two-dimensional tensors have the respective names vector and matrix. All larger tensors are simply described as tensors. Are there actually use cases of larger dimensional tensors? Yes, there certainly is. Here's an example. A grayscale image is clearly a matrix, easily represented by a matrix. A color image adds a third dimension where there are three two-dimensional matrices, one each for red, green, and blue. So that makes color images a three-dimensional tensor. And typically we process neural networks using mini batches, and if we do a mini batch of color images, that list of color images adds a fourth dimension. So a list of color images is essentially a four-dimensional tensor. One Python library that is well suited to describing and using arrays of numbers is NumPy, and the scikit scikit-learn machine learning library actually uses NumPy for doing calculations. However, the tensors as implemented in PyTorch are more powerful. Those tensors include gradient calculations integrated into them, and they also support use of GPUs for faster calculation. So in the rest of this video we will focus here on PyTorch tensors, but if you're used to using NumPy, you will find much of this looks very similar and very familiar. Okay, let's start using PyTorch. Obviously, first make sure you have PyTorch available. Either install it on your own system or use one of the publicly available online Jupyter Notebook services. This link at the PyTorch website tells how to install PyTorch on your system locally. And this article reviews some of the available online Jupyter Notebook services. We will be using the Jupyter Notebook service provided by Google called Colab. PyTorch is already installed in Colab, so we simply have to import the module to use it. So import torch. Then we can start creating some tensors. Typically you would create tensors from data sets available through PyTorch or by converting your own data into tensors, but for now we simply want to demonstrate the use of tensors, so we use some basic commands to create some very simple tensors. We can create tensors from a list, so here's creating a list-based tensor using torch.tensor, and then the list in the parentheses to create the corresponding tensor. And this is just like the two-dimensional matrix tensor that we had before. Note that the output is labeled to indicate that it's a tensor. What this specifically means that it's a PyTorch tensor object, so it's an object within PyTorch that performs just like math tensors, but it has the various features provided by PyTorch, such as supporting gradient calculations and supporting GPU processing. We can also create tensors filled with zeros or ones or filled with random numbers. So here's the command to create a tensor filled with zeros, torch.zeros, and in the parentheses we include information about the shape of the tensor. So number of rows and columns, 2 rows, 3 columns. So here's a tensor filled with zeros consisting of 2 rows by 3 columns. And torch.ones creates a tensor filled with ones. In this case we created one with 3 rows by 2 columns. And finally torch.rand creates a tensor filled with random numbers, and in this case we have 3 elements by 2 rows each by 4 columns. An important attribute to be familiar with to understand the shape of the tensor is the appropriately named shape attribute. So if we take our previous t_rand tensor and enter t_rand.shape, PyTorch will report the shape of that tensor, and it correctly indicates we had created a 3-dimensional tensor with 3 elements of 2 rows by 4 columns. Note that the dimensions of a tensor is referred to as its rank. A 1-dimensional tensor or a vector is a rank 1 tensor. A 2-dimensional tensor or matrix is a rank 2 tensor. A 3-dimensional tensor is a rank 3 tensor, and so on. Now let's do some math with tensors. For example, let's add two tensors together. As you can see, they add together element-wise, so 1 plus 5 equals 6, 2 plus 6 is 8, 3 plus 7 is 10, and so on. Again, adding together element-wise. Let's demonstrate the same tensor addition in PyTorch. Here it is. We define the same two tensors and then a very simple compact equation, add them together and output and evaluate the result. And here we show the same output for the tensor in PyTorch, for adding the tensors together in PyTorch. Let's try adding a scalar, that is an independent number, which you can consider a zero-dimensional or rank 0 tensor. Let's add a scalar to a tensor. Here we add 3 to our first tensor from before, and here is the resultant output. So we've the original first tensor was 1, 2, 3, 4, and we add, so the addition of a scalar adds element-wise as here as well. So 3 is added to each element. The same kind of thing applies to multiplying a tensor by a scalar. So here we are taking our prior tensor 1, 2, 3, 4 tensor, multiply by scalar 3, and we get a resulting tensor 3, 6, 9, 12. Again, multiplication happens element-wise. The same kind of thing applies for raising a tensor to a power. That is, the power operation is applied element-wise. So if we want to square our tensor, each element is squared. So our prior tensor 1, 2, 3, 4 results in squaring each element 1, 4, 9, and 16. Recall that neuron processing involves summing weighted inputs, and then the result is run through an activation function. Note that the same performance applies here as well. When a vector is processed through an activation function, when a tensor is processed through an activation function, the operation is applied to the tensor element-wise. Just like with this squaring operation, if we had an activation function that we were running through, running the tensor through, the activation function would apply element-wise. Earlier we noted that matrix multiplication is an important part of neural network calculations. There are two ways to do this in PyTorch. You can use the matmul function, so torch.matmul, and then in parentheses the two tensors that you want to multiply, or the two tensors you want to do matrix multiplication with, and here is the resulting output tensor. Or you can use the matrix multiplication symbol, which is the @ symbol. So here it is, t first at t second is t first matrix multiply times t second, giving the same output tensor. Previously, we showed running an input signal through a neural network where a vector of input signals was multiplied by a matrix of connection weights. And let's go ahead and repeat that calculation using PyTorch. So here we create our input signal vector using torch.tensor with a list, and then we get our 7, 8 input vector, and then and assign that to input X, and then to W we create the weight matrix tensor, torch.tensor, using a list, and here is the weight matrix tensor as we had it before. And then finally we perform the matrix multiplication operation, so the weight matrix multiplied times the input vector gives the output vector, and the viewer can go back to earlier in the video and confirm that we get the same results here that we had with the previous calculations. So notice how compact and readable that is. Instead of doing nested for loops, you have this nice compact readable equation implementing matrix multiplication, so implementing neural network calculations. So there is other math that can be done with tensors as well, but we have covered most situations that are relevant to neural networks. If you find you need to do additional math with tensors, you can check PyTorch documentation or do a web search. Another important operation in PyTorch with tensors is being able to index and slice tensors. This allows you to examine a subset of your data to perhaps better understand how the data is constructed. Indexing and slicing tensors in PyTorch works the same way it does in NumPy arrays. Note that the syntax is different from Python lists. With Python lists, a separate pair of brackets is used for each level of nested lists. Instead of PyTorch, one pair of brackets contains all the dimensions separated by commas. So let's go through an example. Let's use our previous t_rand tensor and find the second element, first row, third column. So second element, first row, third column, that would be 0.2827. So here's the t_rand tensor, and here is indexing that element, second element, first row, third column. Don't forget, indexing starts at 0, so that is, second element is element index 1, first row is row 0, and third column is column index 2, and there it is, 0.2827. Let's look at a slice of second element, first row, and second through third columns. So here is that in the slicing nomenclature, and here it is. So second element, first row, second and third columns, 0.1816, 0.2827, and here it is, 0.1816, 0.2827. Note the different nomenclature, one pair of brackets, all of the dimensions separated by commas. Let's look at the entire, let's look at another example where we look at the entire third column. And here's the correct nomenclature for that. So column, colon, comma, 2, index 2 for the third column. And there it is. So the entire third column. And note that these numbers match these down here. So in this example, we're using the standard Python convention that a blank before a colon means start all the way from the beginning, and a blank after a colon means go all the way to the end. So a colon alone means include everything from beginning to end. So this syntax indicates that we're slicing and selecting from all of the elements and all of the rows, but selecting just the third column. So a common use for slicing might be to look at individual images in a list of images. So if we could imagine that, if we pretend for a moment that our trand tensor that we've been using was actually a list of images, and that each of these matrices was actually an image, we could actually index to look at each of these individual images. So take the tensor index and look at the first element, index 0 for example, and that shows the first matrix. And if we wanted to look at the last array, the last matrix, the last image, we would say trand index -1 to count back from the end of the list of elements. So using these smaller tensors for demonstrations of indexing can be instructive, but let's do it for real. Let's see it in action for real data sets with real images. So some of this we won't go into in detail. This is just setting up. Since our objective is to demonstrate the usefulness of indexing and slicing, we won't go through this in detail, just use this as setup. So basically this imports a variety of modules that we'll need to import the data sets, and then these last two lines, this first line imports a transform module that allows us to write a function. In this last line we create a function that will allow us to convert tensors into pillow library images. So this command downloads the Caltech 101 dataset. This is a collection of over 8,000 images in 101 different categories, and this is one of many data sets that PyTorch has included in their system. So using datasets.caltech class, using this command, we download the data, and what this does is create a dataset object, which is essentially a container for the data. And these objects can be indexed like lists. So if we want to find out how many elements are in it, we can do a length command, just like in a list. Do a length command on that dataset object, and we find out there are 8,677 items. And if we look at the first item, for example, if we index number 0, we find out that the first item, if we look at the type of that first item, we find out it's a tuple. And if we then do a length operation on that tuple, that first item in the data set, we find out that there are 2 elements to that tuple. And if we look at the types of if we look at the typing of each of those elements of the tuple, so here it is, the first element in the data list, and then the first element in that first element of the data list, we find out that that first element is a tensor. And if we look at the second item in that first item in the element in the list, it's an integer. So what these tuples are, it's a pair of things. It's the image as a tensor, as it's indicated here. It's a tensor followed by an integer code which corresponds to the images category. So through indexing the data set, we've been able to identify its structure and see how the data set is organized. We've noted that it's a list of 8,677 items, and it's a list of tuples, and we've been able to identify that each tuple consists of a tensor, and which represents the image, and an integer which represents the images category. Colab has a convenient function called display, which will display images. So if we want to start looking at images in this data set, first we use the conversion function that we created earlier to convert the tensor into a pillow image library image, and then we can display the image. So we use the function we created earlier, convert to pillow image library, and we operate that on, for example, the first element, and of course, so the first tuple, and the first element of the first tuple is the tensor. That's the image. So convert that. So we convert that to an image, a pillow image library image, and assign that to the variable image, and then display it. And there we have the first image in the data set. Obviously that image is an image of a person's face. We can do the same thing with other randomly chosen elements in the data set. So let's just arbitrarily choose element 1, 2, 3, 4, and again we want to look at the first, in other words index 0, the first item in the tuple, which is the actual tensor, the actual image tensor. Convert that tensor, which this indexing selects, convert that tensor into an image using this function, and then display the image, and we get apparently that image is of a motorcycle. And we can do it again, again arbitrarily choosing item 4321, again looking at the tensor and converting that to an image, and then displaying in the image. And in this case, this image is of a mug. So as you can see, indexing can be quite useful for examining how the data is organized and examining the data to understand its contents. So here's what we've learned. We've learned what tensors are. We've learned why tensors are key mathematical objects for describing and implementing neural networks. We've created some tensors in PyTorch. We've done math with tensors in PyTorch, and we've done indexing and slicing of tensors in PyTorch, especially to examine images and data in data sets. We hope you have found this video review of tensors and their relationship to neural networks useful. We wish you happy coding.